All right, so my name is Ryan Boyd, and this is Michael Manicherry, and we're here today to talk about crunching big data with Google BigQuery. You can reach us, and we removed it from this slide, but we both are actively using Google Plus and actively using Twitter. If you can't find us, let us know afterwards, and we'll let you know what that is. So if you have any questions after this event, you come up with something, you're dreaming all night long about working with big data, feel free to send us an email in the morning and let us know what questions you have. All right, so Google has lots of big data. So here I try to use a remote without actually hooking the remote into the laptop. Yay, so big data at Google. There are 72 hours of video uploaded to YouTube every minute. There are 100 million gigabytes in the Google search index, and that was in 2010. So we're very familiar and work a lot with big data. This data gives us an opportunity to go from the data to true meaning behind the data, to improve our products, to use the information that's out there on the web and the information generated by our products to keep on iterating on them and improving them. But in order to do that, we need to provide an easy way for the thousands of product managers and engineers at Google to express their analyses in a way that they understand, in a syntax that they understand. And many of them come from backgrounds with relational databases and they're familiar with the SQL-like syntax. But not only does it need to be easy, it really needs to be fast. So if you think about this, we need to be able to scan over huge amounts of data. So 100 gigabytes in 10 seconds is probably on the slow end for us. But that's the type of data that we need to be able to really go over quickly in order to iterate on our business decisions. We're in a fast-paced world. We need to be able to push out new product changes really quickly. And so we need technology that allows us to understand how our products are being able to be used just as quickly. Now, it used to be that when you wanted to run an analysis like this, an aggregate analysis of how things are being used, how your products are being used, how your data centers are performing, how ads are performing, you would load your data into a relational database. And the relational database would scale vertically. You could add more CPU, you could add more memory, you can add faster disks. But eventually you get up to the point that relational databases are optimized for performance based off of indexes. They use indexes on the data in order to return your results fast. So as long as the data that you're trying to query is in those indexes, it's pretty quick. But when you're trying to do these sort of ad hoc iterative queries where you don't know what you're going to want to query next week or next month or even tomorrow, you can't build indexes that cover all of that. So you come to the limit of scale. Google looked at this and said, well, we don't just have a single server. We have tens, hundreds, thousands of servers around the world, and we can use those servers in order to crunch our data. But we had another challenge here. Typical big data processing technologies, including some of those that Google developed like MapReduce, are based on a batch paradigm. They're based on the idea of you put in your request and you get your results back in sort of minutes or hours or in days in some really odd cases. But it takes a long time to run these queries. This really doesn't fit with how fast we need to be able to make business and technology and product decisions. So we said, all right, what if we embrace the concept of the full table scan? And we are able to parallelize full table scans across those hundreds of thousands of machines and get results in seconds, not minutes, hours, or days. So let me give you an example. So this talk is going to cover some of the underlying technology, which is based on internal technology, but I want to give you an example on the external technology called BigQuery here. And we're going to do some regular expressions on 15.7 billion rows.
Only 15.7 billion rows?
Only 15.7. I'm sorry, Michael. So let me prove it to you here first. I'm going to, maybe if I could go into the presentation, that'd be better. All right. So I'm just doing a simple select count from these tables. I have 13 tables here. And I was trying to do all of 2010 but in order to get to the numbers I wanted, I had to go to 2011.
So this was a live query over multiple tables. And what are these tables? These are the Wikimedia page view tables, right?
Yeah, so this is basically a record of all Wikipedia, actually all Wikimedia projects, but most of it's Wikipedia page views. Originally they're by hour, and it goes back for about 5 years. So it's every page in Wikipedia and how many times it's been viewed by hour. I've actually kind of pre-aggregated some of this data and made it into by day. Used Compute Engine, which is a kind of service in Trusted Tester right now, and Hadoop running a Compute Engine to pre-aggregate that data. So these tables right now represent by day each of the page views in Wikipedia, but we can see here there's 15.7 billion rows in the tables that I'm querying. And let's say that we wanted to do some analysis of that. We don't want to just count the number of rows. That's kind of boring.
And it's easy. You can do that with a relational database.
Yeah, 15.7 billion. Not hard. Come on. So what we're going to do here is get the title of the page and then the total number of views of the page during those 13 months that we have here, represented each month started into a table. And we're looking for pages in Wikipedia where the title does not contain a colon. So it's not one of the special Wikipedia pages. There's like user talk pages and all these strange special pages. So we're looking for regular pages. And it's Wikipedia, the language is English. And then we're going to do this regex. So we're going to take the title and we're going to say, find me the pages with a title that starts with a capital G, has 2 lowercase o's, and ends with a lowercase e. Group by the title, and order by the views descending. Now, the thing I have to emphasize with this, most of you aren't sitting around trying to crunch Wikipedia data. It's not a very profitable business to be in. But you may actually have things like web analytics logs, gameplay activity logs, marketing data, ad views and clicks data, and that sort of thing. And this data is very analogous to that, any sort of transactional data based off of time. So we can see here the top Wikipedia page was Google, with, who would have guessed that, with how many, what are we at here? 199, so 17 million views. And then we have Good Luck Charlie, Google Chrome, Growth Hormone, Gastro.
Yeah, so a lot of people are looking for reflux disease. Maybe there is a business model for this.
But the important thing I want to emphasize here is this keeps on cutting out, sorry. Our query here took 31.2 seconds. 31.2 seconds and processed 665 gigabytes of data. Now that's 665 gigabytes of data just in the columns that we accessed. These tables are actually over 1 terabyte worth of raw data in these tables. But 31.2 seconds, it's performing that live regular expression, and I could always change this regular expression here, and rerun this query, and we can see this, the iterative nature of being able to run queries in here.
And there's no indexing involved too, right? So you don't have to re-index your database to get this kind of performance. It's running another table scan over the data. And if you had a non-relational database, you may have to actually express this as a MapReduce. There are tools that do this as well using a SQL syntax. They're batch processes. So this hits a lot of the high points, the best of all these technologies.
Yeah, so 31 seconds running regular expressions on 17.5 billion rows. For those DBAs out there, does that give you a heart attack? A full table scan on a terabyte of data? So this really demonstrates the power of BigQuery as a technology. Now, all of you are still a little bit asleep here. Are you excited by this? Come on. All right, so 15.7 billion rows, 1 terabyte of data in 13 tables. It took us 30-some seconds. It took me 20 seconds earlier today. There's some variance there, but it's a very, very quick analysis over large data sets. All right, so I want to give you an overview.
Do you have a question?
So is that all stored in memory somewhere on vast servers?
No,
or is
it's
that
on disk.
in disk reads?
We'll talk about that in a second.
So we're going to give an overview of the BigQuery architecture, but it is not caching. It is pure reading off of disk, all of that data. So we're going to give you an overview of how BigQuery queries are processed and cover that question as well.
then talk about developing with BigQuery, give you an idea of some of the new features that we released in the last couple of weeks. We were out at Strata London and announced some new features there. And then give some time for Q&A if you don't have any questions that come up during the talk here. So the general architecture. According to a 16th century Italian philosopher monk, if you do a full table scan over a 1 terabyte table, you're going to have a bad time.
Wait, I asked you this before. If it's anonymous, how do you know it was a 16th century monk?
Because they admitted their identity to me, but I'm not allowed to tell their identity to you.
Yes, you have a database of it. So.
I'm sorry. It's encrypted, no access. So, if your goal is to actually perform a 1 terabyte table scan in 1 second, here's the type of activity that you need. 10,000 plus disks, 5,000 processors. Not type of architecture that you guys have sitting around idle usually, I would think, underneath your desks. But we do that sort of thing. So I want to cover, before diving into how BigQuery works, I want to cover MapReduce a little bit, which is a technology that some of you might be familiar with, at least at the high level. And basically the concept here is MapReduce is flexible, but it's a little heavier weight. And here's how MapReduce typically works. You have a master node that runs the coordination. It constructs a plan and maps out each of your tasks. So you form up a list of tasks that you're trying to do. They go to the mapper. The mappers perform those tasks. And they're reading and writing from distributed storage. As they're reading in these tasks and as they're writing out the results of the tasks, there's a lot of reading and writing going on in the distributed storage. And then there's kind of this 3-step process, which is actually a shuffle in between to order your data, and then it gets passed to reducers, and those reducers kind of combine the results from multiple mappers together to produce your final result. But the key thing here is what's in the center of this diagram is this distributed storage. There's a lot of disk activity which happens. And even a lot of the large companies that I've talked to that run MapReduce in production are running it on, say, 40, 50 nodes, things like that, a relatively small amount of machines. And the disks on those machines can only be so fast. And the worst part here is that oftentimes when you're trying to run some sort of queries on a MapReduce framework, even if you're using Hive, which provides a SQL-like syntax on top of MapReduce and Hadoop, you're going to have multiple stages of maps and reduces. So it's going to just, basically that disk becomes the bottleneck of all your operations.
And the shuffle sort, you may have multiple shuffle sorts, right? You may be piping the result of one thing into another shuffle, and this can happen over and over with a complex query.
All right, so Dremel, which is the underlying technology for BigQuery, is architected a little bit differently. The distributed storage is at the bottom here. And the distributed storage, the only time that this is accessed while running your queries is to read the data off of disk. So each of these leaf nodes gets assigned a chunk of data to read off of that disk. Things on the order of tens of megabytes of data that each of the cores on these leaf nodes are reading off of the distributed storage. So there's only that one read at the very beginning. And then there's this long-lived serving tree. So typically with a MapReduce framework, you're starting up JVMs for each of these things. Oftentimes people, if they do want to use many, many machines, are actually just launching them on something like Amazon's Elastic MapReduce and basically kicking them up when they're trying to run their queries. So they're very short-lived. So there's a lot of overhead in setting up and tearing down the process. The architecture of Dremel really relies upon the idea of this long-lived tree that processes the results. And then, as things go up this tree, so the leaf nodes will kind of do the first level of the query, restrict things off of the where clause, find the results, and then as it goes up the tree, the mixer will combine multiple leaf nodes results. So think about something like if you're trying to get the count of records, the two leaves will take the counts of the records that they're responsible for, and then the mixer will actually do the sum of those two counts as it goes up the tree here. But we're really relying upon the diskless data flow. We're really relying upon the idea of Google having a super fast network backbone for all of this data to travel over, and only that one single read from disk. We'll talk about the columnar storage thing here shortly, but that's another important part about this architecture is limiting the amount of data we read. So the columnar storage. Typical databases will store in a record-oriented storage, which is great because you're keeping all the data in any individual row together. In a column-based storage, you're basically keeping the data in a column, column by column basis. And this is really important for Dremel and BigQuery because what we do is actually only read the data off of disk that represents the columns you're accessing. And most SQL queries are only actually accessing a small number of the columns in any given row. Not only is it faster because of this, but it also tends to be more compressible because the data in any particular column is much more similar to the other data in that column than it is across an entire row. All right, so let's talk about BigQuery. The big important thing to remember about BigQuery is it is an API. BigQuery is an API. It's offered as a service. It is not intended to be an end-all business analytics solution or business intelligence solution. It is an API for you guys to build your internal dashboards or build products on top of. And we have people doing both of those with BigQuery. So if you think of things like the marketing analytics stuff or logs analysis that I talked about earlier, gameplay analysis, we have people using it for systems infrastructure monitoring, sensor analysis, a lot of different types of use cases, but they're building applications on top of it, rather than just kind of having their data analysts use it on a day-to-day basis. So to get your data into BigQuery, it's really this two-step process. You first take your data and you upload it to Google Cloud Storage. Google Cloud Storage is very similar to something like S3. It's actually protocol compatible with S3, and so you can upload your data there. We store it, we take care of the data, and then you tell BigQuery to take the data from Google Cloud Storage and bring it into BigQuery.
Do you have to do anything to structure data going into your cloud? Do you have any requirements as to how you to structure that?
We'll get into that here shortly.
Okay.
Yes. So when you load your data into BigQuery, basically, I said you had to take the data off of Google Cloud Storage and bring it into BigQuery. You basically construct what's called a job object. So it's a REST-based API. You create a job object, and that job object indicates the Google Cloud Storage URL for the data that you're loading into BigQuery. And then you just post that job object to the jobs endpoint, and we insert that as a new job, and then do that loading in an asynchronous fashion. And then when you're ready to query, you're creating a job object again. You're doing the exact same thing we did earlier with the job object, except in this case you're defining a query job. And your query job has this SQL-like syntax in it, which you can then use to define your query. And you can get the results here asynchronously, but you can also get the results synchronously. If you want to have a hanging request to get your results, you can do that, and it's useful in some types of applications.
One thing to note is the response to these requests provides a job ID, which you can use to then reference your job. So you can check if it's still pending, or once it's done, you can get the results back afterwards.
Yeah, and you also get a list. We don't purge those job IDs that often. You can get a list of a lot of your past jobs and look through all your previous queries and see how long they took and that sort of thing. Sure.
Is there a dashboard like App Engine for these, or are they all requests that you make yourself with job states?
There is the interface that we showed earlier for that will give you basically a list of all your data sets and the tables in those data sets, and you can look at your queries there. It's only queries that you're executing within that UI. We don't expose all the queries from your project. It'd be fairly easy to. It just hasn't something we've been working on.
That interface is useful for running sample queries and things like that, but it's not fully featured. We also have a command line client that has most of the features available in the API, I believe. So if you want more fine-grained access, that's a good tool to use.
Okay.
So we do have a number of libraries in your favorite programming language. Hopefully your favorite programming language is listed here. Is anyone's favorite programming language not listed here? What's your favorite programming language?
XQuery.
XQuery? Okay.
We just had a question on Stack Overflow about Erlang. Any Erlang hackers in here? Okay, yeah.
Not have a library for that yet.
So it's standard REST-based API calls, so you can write these in most any language, but we do provide libraries that make it a little easier. Here's an example using the JavaScript library, and we can see here at the top we're just basically defining our query, defining how long we want to wait potentially for the query to return, and then we're executing the query and just using jQuery to loop over each of the elements of the result, which comes back as JSON. And calling that function on those result items. So fairly simple. Pretty much every application that I've built with BigQuery in terms of the code to run the queries and get the responses back and do something with it, somewhere between like 50 and 70 lines of code at max. And I can show you some of those later here, but it's very easy to use these client libraries to run your queries. So preparing your data. Get to this gentleman's question here. The first thing that we want to talk about is denormalization. So you were all taught probably in database class in college to always normalize your data, to break it up into multiple tables. Well, we don't do that with BigQuery. We denormalize the data, and that produces a lot faster query response times for you because the joins can be very expensive. BigQuery does support some joins in the smaller end, if you have simple lookup tables and that sort of thing. But we don't support sort of huge table joined to another huge table. In that case, you should pre-join it, denormalize the data as you're loading the data in. You can load your data in CSV format. I hope this doesn't remind you too much of the 1960s or 70s or something. It certainly does to me. It's kind of an antiquated format, but it's very simple, a way to specify your data in a very readable, simple way. And it's fairly lightweight if you don't go down to basically compress this data. It's fairly lightweight overall. Though obviously some of the binary formats and all nowadays are a little bit more lighter weight. Now you can take your relational data here and make it into the denormalized form, or you can make it into sort of a nested form. In many cases, with NoSQL databases and all nowadays, a nested repeated format is quite common. And so BigQuery, as of 3 weeks ago, 2 weeks ago, something like that, we now support nested and repeated data. So if you have something like this where you have a name, age, and gender, and you want to have a list of all the cities that person lived in, you can do that and have that sort of nested and repeated underneath the one record here. In order to express your data in a nested and repeated form, we've added support for JSON, a much more modern data format than CSV. Now JSON has great benefits to it in that it's very expressive. You can easily read this. You understand what each of these fields are, and you can do the nested and repeated data. It does have some, side effects from that though. Is that you're repeating the names of the fields over and over again throughout this data. So the uncompressed version gets to be kind of large, but you can compress that and make it a little bit smaller.
My favorite thing about it is you don't have to worry about ordering so much. You have your fields labeled, so you actually can change the order compared to your schema. Whereas CSV you can't, right? You actually have to have it in order that matches your schema. That's my favorite thing about it.
Yeah, and we also do some things that are kind of cheating in order to optimize for JSON. So we support a new line delimited JSON, which is what we mentioned here. Now, what that means is that every single at the end of every single row represents a single record. So you don't have any new lines within your data, and then you just have a new line at the end of every row. And so think about this kind of compacted all into one row here. And what that allows us to do is parallelize the loading of your data across a bunch of different machines. So to give you an idea of performance on loading data, I took 3 terabytes of data. Now this wasn't in JSON, but 3 terabytes of CSV data, loaded it into BigQuery. It was already sitting on cloud storage. I loaded that 3 terabytes in 36 minutes, and then was immediately able to start querying it because there's no index building, none of that. So after 36 minutes, I was able to query on this 3 terabytes data as if it's been sitting there for weeks or months or years and already had indexes like a relational database would do.
Another cool thing about this is that we mentioned this earlier, but if you're using a document store already, chances are you've modeled your data in a format that looks something like this. Yes, I mean, that's possible. And I was playing with Mongo a little bit after we launched this feature to test it out. And, you can use like something like Mongo export to export your data in something like this. I wrote a Python script that actually made new line delimited JSON as well. So it's pretty easy to have interoperability with some of your non-relational databases.
So actually, this brings up an important question for the audience. What other data formats do you guys use for your data? For transmitting and storing your data?
How about Avro? Anybody using Avro? Familiar with that format? Apache Avro? It's great.
It's more of a binary format for representing large data, and it has similar benefits as we get from adding the new line delimited part of JSON. Is that it's very easy to parallelize the loading of an Avro.
What about XML? People work XML?
Yeah.
Does that work, or is that not recommended these days?
We don't support XML for direct ingestion into BigQuery. I've written plenty of code which takes XML, like the Wikipedia data is actually XML. I take it using Python and a streaming parser and create CSV or JSON out of it. But yeah, I mean XML has the heavyweight, but it's also kind of complex in many ways too. As soon as you start having to deal with namespaces and all that, so.
Yeah.
Protobuf?
Protobuf, yeah.
Is it more good or not?
Yeah, that's what
But if you have use cases where you think it'll be really important, definitely let us know.
What's the meaning of the new lines in this?
The meaning of the new lines here is just to separate rows. So this in this case represents one row of data. Imagine, if you will, this compacted onto one line of text on that screen.
So a row may be just a label. Mother substance use is a row.
So no, this whole thing is one row. So this data actually represents a baby born in the United States in our natality birth statistics data. So each baby born has a year that they were born, the list of states that their mother lived in prior to the baby being born, health scores, etc. So this all represents kind of one transaction. We can call birth a transaction. And so in between each row, you would have a new line.
you are such a Googler.
I'm calling a birth a transaction. I don't know if that's, anyway, we're not going to go there. But so you would have like a new line character, a /n at the end of this. And this would all be kind of crunched onto one row if you looked at the file in a text editor or something. All right, so when you want to go query your nested and repeated data, there is a very simple way to do it, and that's just kind of referencing, so this mother substance used, we reference .alcohol, is just saying the alcohol property is true in mother substance used. That's kind of a very simple query on the nested data, but then you can actually do some more complex things as well. And that's if, for instance, you wanted to actually count the number of states that a mother lived in each of these rows, and then take an average of those number of states. So, for instance, that you want to take the average number of states that a mother lived in that smoked versus the average number of states a mother lived in when they didn't smoke, and analyze the difference between that. I'd be curious as to whether there is a difference there. But there's so this kind of gives you enhanced operators. We also do support in that within record statement the ability to get ordering. So you could say, what is the first state a mother lived in, or the last state a mother lived in, or something like that, which is much harder to do in a normal table.
That's right. That's one of the main advantages of using, if you have a choice between a flat and nested or repeated, generally these kind of queries that Ryan is talking about are much simpler to write when you use the nested model. You can write equivalent queries using a flat normalized model, but oftentimes you're doing subselects and it's very complex.
Does the fact that you're structuring the data more naturally actually make your queries better, faster?
No,
Or
but
not?
it doesn't make it worse.
Got it.
In general, the BigQuery and the underlying Dremel technology is really good at handling these nested and repeated data sets, and that's one of the primary reasons it was created. But your storage, the underlying storage, is actually still that column-based data storage for each of these properties. So it doesn't make it worse, which is a great benefit. So you can still structure it in a way that you understand without making a worse performance.
It sounds a little hand-wavy, but sometimes it is good to model the data in something you're familiar with, rather than like artificially demodeling performance reasons. Good question.
All right, so when you come to actually querying the data, I'm sure our AppScript team is located in New York. So how many of you have seen a presentation given by our AppScript team? Only a handful. Wow, I'm surprised.
Meetings more often than 3 times in the last 14 months.
Oh, wow. Okay. Well, for those of you that haven't, you should definitely come and meet the AppScript team. There's even some new members out here that moved out from California. They're a really awesome bunch of folks. But what I want to show you here quickly is, again, looking at that birth statistics data. And I have a single little button here that I'm going to press, Run Query Run. And this is going to get data from BigQuery. It's a 137 million row table. And we're taking the results of that table, aggregating them to figure out on a per year and per color of state the average age of first birth and the average weight. So this was just a little personal experiment. I wanted to figure out, how these numbers differed in red states versus blue states.
But Ryan, is it statistically significant? I see that every single time.
I can have fun with data without it being statistically significant.
Somebody knows how
Not
to
publishing this in a
run the
journal.
numbers.
So what we're doing is we're loading all the data. There's 72 rows, I think, here of data. And we are then graphing it out. The graph is actually based off of a pivot table, which I have defined over here. But so we were able to create this pivot table, create the graph within a tool that we already understand. For those of you that don't understand Google Spreadsheets but understand Microsoft Excel, we have very similar functionality that we just released, which is the Google BigQuery connector for Excel, which does basically this. And we can see here that we look at from 1970 on through 2000, the mothers are giving birth earlier in red states than they are in blue states, and the gap is pretty much widening as you go on. Now this is using the red state, blue state data from the 2008 election, so it's just 1 year of that data, but it's still kind of interesting to look at this. And I've done some other things with regards to like birth weight of babies where the mother smoked. It's about a half a pound lighter than the birth weight of babies where the mother did not smoke. So there's all sorts of fascinating stuff to be discovered in this data, even if it may not be statistically significant.
Well, maybe. I'm just wondering.
There was did I see a question over here?
Where is the query?
Yes.
Defined or special?
So that button is actually calling what's called a Google App Script. Google App Script is a server-side JavaScript execution environment. So it's JavaScript code that runs on Google servers. Here's where the query is defined. This query is taking advantage of some very manual optimizations to make it faster. And so if I showed you the query I wanted to run, it would kind of highlight a bug that we're working on fixing. But in the end, this, even after that super long query, we only have 68 rows of code or lines of code here. And this is handling the OAuth authorization, it's handling the running the query, looking at the results, populating the spreadsheets with the results. So you can do all of this fairly simply with using those libraries.
We also have this almost the exact same code online in a tutorial from the AppScript site. So if you're interested in learning more about it, this is a great way to get started.
And Michael actually just did a video this morning with Ikai from our AppScript team talking about how BigQuery can be used from an AppScript. And so it's like, I don't know, a 20-minute, half-hour video.
We basically go through the process of building something like this. And I wanted to say one more thing. We actually use this internally. So there's some teams at Google that are building like applications just with AppScript and BigQuery, because it's fast, easy, gets the results. And it puts the results in a spreadsheet, which is oftentimes where your analysts want the data anyway. So it's very useful.
Sure.
How is this suited for sensitive data? Are there any security guarantees or?
You'd have to read the terms of service yourself, which is, I'm sure, a line you've been used to hearing from Google. We do, in BigQuery, we have all of the machines that Google has and their current performance characteristics and stuff like that. We use it for our own data. The other thing that I would say is that it's using the same sort of Google account infrastructure as all of our other products and the same access control list mechanisms. So you can take your data and you can basically share it just with one of your coworkers. You can take your data and share it with your entire company, domain-based sharing with Google Apps. You can share it with the world. You can do whatever you want, and you give really fine-grained access control on individual data sets. But it's a technology that we trust. Our own data is in the system, and it's a technology that we've opened up some pretty fine-grained controls around for you. So I can't make absolute statements in any way, but I certainly have no hesitancies about people storing data. We actually have the variety of customers that are using it. There's a case study that's about to be published, which is a mobile ad network in Brazil that's using it. They happen to be probably considered a competitor if some people looked at what their company does, but they're actually using BigQuery to analyze all their data. So we're not looking at their data. The data is owned by them, and they can run the types of analysis they need.
Okay, that's what I was wondering, if it was subject to the same kind of data mining that Gmail and stuff is.
No, I mean this is basically part of our cloud properties where you're controlling what access is made to your data. So it's considered your private data.
What protections are there for access so that say somebody then try to brute force or otherwise try to figure out how to get the credentials to get in?
I mean, this is based off of the same sort of protections that we have for all of our other APIs. So it's OAuth-based authorization, Google account-based. We have a lot of protections in there. If you grant access to just a particular set of accounts, you can do things like have one-time passwords. Like, if I need to sign into my account to grant access, I actually need to have my phone in addition to knowing what the password is. So you can add additional controls on top of it, and we're relying upon the same protections that we have across Google for that.
Yeah, there's a question over here.
What's the maximum capacity to handle PID-LAN?
How much data do you have?
We haven't run into a customer we've had to say no to yet. Try it. So the pricing is based off of both storage as well as a dollar figure per terabyte query. So the online pricing is 35 cents a gigabyte. It's $35 a terabyte is what it works out to be of the data that you're actually querying. So it's only the columns that you're touching when you're running the query. We're doing full table scans on every query. You can shard your data so that oftentimes if you're only querying over the last month worth of data or the last 6 months, you can shard your data based off of that, so you have smaller query prices. But yeah, we definitely haven't run into anyone that we've said we can't handle their size of data, so let us know.
What's your maximum largest customer base?
I don't have that information.
One thing that's good, you guys like the columnar data store, that's another thing that's an advantage of BigQuery, is that's how we can keep the pricing locked to those columns that you look at, because that's how we store the data. It's very easy for us to say, yeah, you're just looking at those columns, so we're only going to charge you for the processing over those columns. So, great.
Is there a free allowance for developers?
There is a free allowance. You can do 100 gigabytes worth of query results in a month as a developer across our public data sets. And those public data sets include things like this burst statistics data, some Wikipedia data, some weather data, a variety of different types of data sets.
We have GitHub commit.
GitHub commit.
That's the funnest one.
Looking for profanity in GitHub commit messages can be fun. So yeah, there's a variety of public data sets. You can't load any of your data in, for that. You have to pay if you want to load your data in, but the storage prices are fairly cheap.
Eventually, can you make edits?
It is an append-only data store. It's really meant for analytics. So you're not able to make edits to your data. We do have people that will delete tables and re-import tables. If that's all you're doing with it, it's probably not a good use case for the product. But if that's something, one of your tables you want to just keep up to date, with the current state, that's fine. Most of the data that BigQuery is good for is sort of transactional records where you don't really need to edit the data.
You really have to, so the workaround would be using app scripts?
The workaround, if you're trying to edit your data, would be to delete the data set and re-import, or delete the table and re-import the table with the updated values. It's append only because of basically the performance characteristics we achieve are only achievable with an append only style data store.